Well, we're continuing on in equilibrium here, in two-dimensional equilibrium, and today we're going to talk about springs. Now, if you remember from chapter 3, when we talked about springs, we recognize that the force in a spring is F is equal to Kx, or S. And I'll call it S as the stretch in the spring. Remember that the length of a spring is equal to the unstretched length plus the stretch. So with those two kinds of things, what we're going to do is model the new displacement of these scenarios to try to figure out what the new position might be as we stretch a spring. Okay, so here's a problem. We have a spring constant on this side of 1 and a spring constant on that side of 1.5. We obviously have a distributed load here. Let's go ahead and put the resultant of that distributed load, and I'll just call it R, and that's going to be equal to 1/2 BH, so 1/2, the base being 3, the height being 600, so R is going to be equal to 1/2 times 3 times 600, which is equal to 900 newtons. It's acting at a distance of 2. The reason is because it goes over 2/3 of this from the skinny side, or 1/3 from this side, so that distance is 2. Alright, let's go ahead and draw the free body diagram then of what's going on with this spring. I know I have a 900, and I have a force in this spring going up. I'll call this FA, and I have a force in this spring. We'll call it FB. Now, as this force is applied, I think maybe you'd agree that both of these strings will stretch a little bit. And this one has a higher spring constant, which means it will stretch less for a given force. This one has a greater or a smaller spring constant, obviously means it stretches more with a given force. Also, the force is kind of weighted to this side, so I can pretty much by an informed guess say that the new position of this bar will look something like this. And I'm going to say this is my starting spot, and this is the displacement of that spring, so I'll say that that is S spring B, and this one will be S spring A. Alright, see if we can find out something here. What we're going to say that there is an angle, theta, and that's really what it's looking for. Determine the angle of tilt of the beam when the load is applied. Okay, let's sum some moments. We can sum the moments about any point, but I'm going to sum the moments about C here and see what I can discover. Sum of the moments about C is equal to 0. So I got minus 900 times 2 plus the force at B times 6 equals 0. So force at B is going to be equal to 300 newtons. And then sum of the forces in the y, I'll go ahead and do that. Sum of the forces in the y is equal to 0. So I have FA plus FB minus 900 equals 0. And I can solve that for FB, or sorry, FA is equal to, am I doing this right? Yeah, FA is equal to 600. Okay. Alright, so now that I have the two forces, we can also talk about the two displacements, which is nice because the forces now are equal to that. So let's talk about point B over here. I'll say FB is equal to KSB. KB SB, this is going to be 300. It's going to be equal to 1.5 SB, so SB is equal to 0.2. Actually, that's this should be 1500. So it's 1.5 kilonewtons per meter, but it's at 1500 newtons per meter. And let's talk about SA. FA is equal to KASA. This is going to be 600 newtons. It is equal to 1,000, sorry, SA. So SA is equal to 0.6. And these are in meters. Okay, now that we have done that, we should be able to do something with trigonometry that might make some sense to help us solve this angle theta. So what we have is that we have this angle right like that. If this is angle theta between those two, this is going to be angle theta here. I can put that there, and this distance here will be SA minus SB. And so, solving for angle theta, I'll say theta. And let's do, we can do tangent or sine. And what I want to introduce you to is a concept called small angle approximation. But let's do the sine. The sine would say that this is 6 meters here, because that beam didn't stretch. So the sine of theta is equal to the side opposite over the hypotenuse, which is equal to SA minus SB, so that'd be 0.4. Hypotenuse is equal to 2 meters. And so that gets us, the angle using the sine is 3.822 degrees. Now, I'm going to introduce you to this small angle approximation such that the tangent could also be used when you have small angles. So let's just use the tangent of theta is also equal to that. Let's say that this distance here is still 1.00 like that. So that would be the side opposite over the side adjacent. That's also 0.4 over 2. And you get, if using the tangent, you get this is equal to 3.814 degrees. So what I'm trying to do is convince you that either the sine or the tangent are accurate enough when we're doing small angles. Again, that's called small angle approximation. So whichever is most convenient using either the sine or the tangent will work. Well, this next spring problem is a little more difficult, but it's a really good real-life kind of problem where you have springs in a mechanism and you want to find out how much force it takes to close perhaps a switch or some other kind of displacement that you want to close. So what our question is we have some spring constants, some two springs. They're 50 millimeters apart. We want to find out what force it takes is required. What force is required to push and close this switch? So what we could guess is, well, first of all, let's draw a Freebody diagram. We're going to say that there's going to be a force required. This is our unknown force. Force at C. And when you do that, it's going to stretch this one. And if it stretches this one, it's going to have a force pulling back up. So I'm going to say that there's going to be a force at B because it's being pulled that way. If it's being pulled this way, this one is going to stretch upward, which means that there's going to be a force pulling down at A. So there's going to be a force pulling down at A. Now, I don't know if that all makes logical sense to you, but these are springs that are going to move in either tension or compression. In this case, they are both going to be in tension. They're both going to be stretched. All right, so if I do that, let's go to our displacement figure, and let's say that this will be the stretch. I'll call this S of A, and B is going to be stretched downward, so this will be S of B. The total displacement on FC will be 10 millimeters, so I'm going to call that 0.010. That's going to be the total height there. This was the equilibrium to start. This would be the starting position. I think that makes some sense. And this is the displaced spot down there. All right, let's see if we can find some forces. Let's sum the moments about B. Sum of the moments about B equals 0. Well, I have positive FA times 50 millimeters minus FC times 50 millimeters equals 0. So I don't know the magnitude, but I do know that FA and FC are equal to each other. All right, how about some other concepts here? Let's sum the forces in the y and see what we get. Sum of the forces in the y is equal to 0. So here I have minus FA plus FB minus FC equals 0. Again, I don't know any magnitudes, but I can discover that FB is equal to 2 times FA. Because these are linear springs, and I know that F is equal to Kx is equal to Ks, I know that SB is equal to 2 times SA. Another key concept here. Once I know that, then I can do a little bit of work. Let's see if we can find out some of these distances by trigonometry. For example, if I started with a displacement, or if I started with this at 1, or 10 millimeters, sorry, I know this distance here is 10 millimeters minus SB. I know that this distance here is 10 millimeters plus SA. I know this total distance here is 50 millimeters plus 50 millimeters, or 100 millimeters. So I can set this up as 2 similar triangles. I'm going to say that this is going to be my angle theta, and I can use either the sine or the tangent, but I'm going to just say sine equals tangent and see if I can write something down that makes some sense. I'm going to say sine of theta equals tangent theta. And for this one triangle, which is right here, I'm going to say that that is 0.10 plus SA. Beg your pardon, this 0.010. There we go, 0.10 plus SA over 0.100, in other words 50 millimeters plus 50 millimeters. That's for this triangle. And again, that's going to be the same for this one. So let's see what that looks like. That is 0.010 minus SB over 0.100. Now I have one equation, 2 unknowns, but I have a relationship over here that I can solve into there. So when I solve that, I get SA is equal to 0.002 meters. Once I do that, I can say that FA is equal to KSA, which is equal to 5 times 0.002. That's 5 newtons per meter. So that's equal to 0.010 newtons, and that's going to be the same as FC, which we already talked about. FA, I beg your pardon, here, let me just change that. FA is equal to FC, and FC was the original thing that we were trying to solve. So that's 0.01 newtons is the total force required.